Okay, recording has, let's see, recording has started.
Okay. Going live. Three, two, one, and we're live.
Hey, good evening, everyone. Welcome back to Amateur Astronomers Incorporated for our Fridays at Home presentations. AAI makes its home at William Miller Sperry Observatory on the campus of Union County College in Cranford, New Jersey. But since the observatory is closed at this time, we're holding our weekly presentations online. So our presenter this evening is AAI member Steve Kozma. And he's been a member for several years now. He's also what we call a qualified observer, meaning he can operate the telescopes at the observatory. His presentation tonight is titled Orbital Traffic Congestion and Space Junk Detours. So, Steve, go ahead and take it away.
Hey. Welcome, everyone, to AI Remote Friday Night Presentation. I'm Steve Kozma, and the topic is Orbital Traffic Congestion, Space Junk Detours. Late January this year, I got a call from my 93-year-old mother living in Pittsburgh. She was concerned and a bit excited to tell me about predictions that 2 satellites were about ready to collide in the skies above her. I tried to calm her down. Then after the call, I read some of the news reports online and realized how little I really know about how congested Earth orbits are and satellites and space junk, and what's being done about it. At one of the later Friday night meetings, I mentioned to Mary Duca that this might make a good topic for presentation with one of the more seasoned members to present. She coaxed me eventually to the presentation. It's frozen. I'm sorry. I got a little problem here with the, okay. Good. So, George, there's a problem on the screen here.
Okay. It looks
Okay.
like it's presenting fine.
Okay. Okay, in the weeks that followed, come to recognize that this is a growing problem with serious implications for a technically dependent global society as a whole, as well as for the future of space exploration and astronomy. As we were warned over 4 decades ago by NASA's Donald Kessler, a true visionary. It's evident that as we, as a global community, for the sake of future generations, must strive to successfully meet the broad range of challenges, which I will attempt to present an overview of. The Kessler Syndrome is a theory proposed by NASA scientist Donald Kessler in 1978, used to describe the self-sustaining cascading collision of space debris in LEO, lower Earth orbit. It's the idea that 2 colliding objects in space generate more debris than collides with other objects, creating even more shrapnel, and litter until the entirety of LEO is an impassable array of super swift stuff. At that point, any entering satellite or launching vehicle would face unprecedented risks of headlong bombardment. What is space junk? Space junk, or orbital debris, is any man-made object in orbit about the Earth which no longer serves a useful purpose. It includes non-functional or inoperative spacecraft, satellites that are inoperative or defunct, scientific instruments that are dead, abandoned launch vehicle stages, upper stages, carriers for multiple payloads, debris during spacecraft separations, mission-related debris, fragmentation debris, such as upper stage explosions, collisions, solid rocket effluents, motor effluents, flakes of paint, thermal stress, or partial impact. On the video to the right is a computer-generated image of objects in Earth's orbit currently being tracked. Approximately 95% of these are orbital debris. Remaining 5% are operational spacecraft. You'll see that the most congestion is in the orbits immediately around the Earth. And there's some areas of congestion further out, what is called the geostationary orbits, geosynchronous orbits. The table indicates a breakout of the various object size categories and the approximate statistically modeled estimated quantities in for each of those categories. So what contributes to the mix in these orbits? Well, since 1957, with the launch of the Sputnik rocket, started the space age. Of all the rocket launches and satellites placed in orbit, there's still 5,500 satellites in orbit. Only 2,300 of those are actually operational. Everything else is considered space junk, including a lot of fragments that were caused by about 500 various events. The total number that can be tracked right now and cataloged are somewhere in the neighborhood of 22,000. How did things get so cluttered with debris in Earth's orbit over the last decades? Well, there are 2 factors involved. One is objects such as defunct satellites in orbit tend to stay in orbit for a very long time, depending on altitude. Could be for decades for lower orbits, could be for centuries for higher orbits. Objects in orbit move at very high speeds, especially in the lower orbits, as fast as 8 kilometers per second or about 18,000 miles per hour. So impacts even with very small items can cause significant damage. Operational satellites can use thrusters to make adjustments if needed to avoid collisions. Dead satellites do not stay in their lane or maintain their exact social distancing, nor stay in the same orbital plane relative to all the other objects. Instead, each defunct satellite and piece of debris is subject to drift and decay, Gravity plays an essential role in establishing the orbital path of the object. Kind of a balancing act is involved. Stronger gravitational attraction, the faster the object needs to travel to maintain its place in orbit. Now, there's variations in the gravitational field over the globe. An exaggerated representation of this is shown on the left of the slide. And that is the reason why you see the drift. Friction of an object with Earth's atmosphere causes decay. Atmospheric drag and orbital altitude in LEO caused by the frequent collisions of gas molecules in the lower orbits. That results in spacecraft reentry. Altitude gets lower, denser atmosphere is there, increases the drag, increases the friction and the heat, and burns up on reentry. Now, the objects stay in orbit for quite a while, depending on what the altitude is. For example, Vanguard 1 was only the second satellite that the US launched into space back in 1958. It's still there, up in medium Earth orbit, which is higher, of course, than the lower Earth orbit. Could be there for another 200 more years, along with two other Vanguards that were launched in 1959. And they're not operating, they're considered as part of the space junk. Small particles of space debris falling out of orbit burn up in the atmosphere, but the larger pieces can wind up reaching ground in chunks. And one statistic I read is about one uncontrolled reentry of a spacecraft or rocket body weighing in the neighborhood of 2,000 kilograms or 4,400 pounds occurs every week. And approximately 10% to 40% of their mass reaches the ground. But since water covers about 70% of the Earth's surface, most debris falls into the oceans or into large swaths of land that are uninhabited. This should give us some reassurance, but then again, in January 1997, a woman walking in a park in Tulsa, Oklahoma, was hit on her shoulder by a 6-inch long crumpled object, about as heavy as an empty soda can, which is found to be a part of a woven material used on the fuel tank of a Delta II rocket, which launched in 1996. Now, lucky her, a couple other big pieces fell, 66-pound titanium pressure tank and 550-pound stainless steel upper stage propellant tank that landed in Texas further on down the road. And to the right, you'll see a video that is a simulation of an event that occurred February 10th, 2009. Two communication satellites collided. One was an active US Iridium-33, and the other was a military inactive Russian Cosmos 2251. Both collided, shattered, sending debris into lower Earth orbit. About 2 years earlier, there was a Chinese anti-satellite test that fragmented and sent about 3,000 fragments. And you'll see some of those represented in green as the video progresses. You see the fragments from 2009 episode merging in with the pre-existing fragmentation around the orbit. So you see how this builds up. And then fragmentation from that earlier Chinese anti-satellite test likely caused the Russian satellite to spin out of control. So from these three events alone, that accounts for about half of the orbital debris below altitude 1,000 kilometers or 620 miles. Now, in March of 2019, India did a similar anti-satellite test, and that sent more debris in, and the saga continues. Now, on the right here, we're talking about the threats to the International Space Station briefly. On the right here, there's a space debris sensor on the ISS, and it collects data on some of the smaller debris that tracking stations just can't see. If surveillance indicates that there's a 1 in 100,000 chance that a known trackable piece of debris, space junk, will enter a protective area, then the performance of damage avoidance maneuver would be done, slightly shifting using the onboard thrusters to avoid path of incoming debris. That's okay if adequate warning is provided. There have been a couple instances where the potential for collision was sensed too late to avoid the maneuver. So the next video will indicate what happens in that case.
Space junk was on a collision course with the International Space Station. Spotted so late, there was no time to move out of the way. Instead, the 6 astronauts got the order for mission control.
The probabilities are still in the red threshold, and we are planning to have you shelter in place.
If all else fails, the astronauts on board the space station can climb into those Soyuz space capsules and wait to see whether a collision actually takes place. If it does, they can in a few seconds detach from whatever's left of the space station and then immediately try to return to Earth.
Mission Control orders the astronauts to the Soyuz lifeboats. It's only the second time a crew has been told to potentially abandon ship.
Once we got all the hatches closed and when we were all buttoned up in our Soyuz spacecraft, there really was nothing to do but wait.
Okay, not to leave you in suspense, but the rogue object was pretty large, traveling at 8 miles per second. It cleared the ISS by about a football field length, and all went well after that. Now, the nightmarish scenario in the detachment scene from Warner Brothers movie, that offers a dramatic representation of what could be encountered if we don't take addressing Kessler Syndrome seriously enough. So we don't have time to show that, of course. Even astrophysicist Neil deGrasse Tyson acknowledged that to some extent, the representation was somewhat realistic, or possibility, despite his slamming on some of the other inaccuracies in the film. And that all got started with satellite collisions and last minute warnings from mission control just before communications got lost. Now, what are the risks to astronomy? Now, most of the earlier launching missions were military based. And of course, we had the NASA missions. Now, more recently, commercial enterprises have gotten involved in working together with the government, which is SpaceX with the launches to the ISS, and also with Starlink and OneWeb, for some of their commercial constellation satellites that are being sent up. Now, while providing greater reliable internet coverage in the most remote regions of the globe is a noble task, there are some trade-offs with sending as many as, right now the count for Starlinks are about 482, and they're being sent up at 60 at a time. OneWeb launched already 74, and they now went bankrupt, so I'm not sure who's taking care of monitoring those. But a number of issues come into play here. One is the number of satellite population is rapidly increasing with these kinds of launches. And they're also causing some interferences with optical telescope images. Some of them, you see tracking lines. You might mistake some of those objects for some other stellar object or maybe even an asteroid or something, but it does cause some interferences because of the reflections. And radio astronomy is also affected. OneWeb, for example, might have some cross-signal interference issues. They may be operating too close to the radio spectrum assignments used for astronomy research. Just to get a sense quickly of where the orbits are that we're talking about, LEO lower limit is about 100 miles up, and below that it'd be difficult to maintain orbital path due to atmospheric density. The slide, as far as on the right, it's a schematic representation of the other main categories of orbits. Talking mostly about LEO so far, the most congested one. The table on the left shows the difference in the population of each of the orbits as far as the number of operating satellites right now. So the advantages of operating the lower Earth orbits is that you're closer to the Earth, so you've got a lot better resolution. If you're talking voice signals, you've got a very short path, almost instantaneous. For human spaceflight, you got short distances back and forth. But there are some issues, such as you don't have as much wider coverage, so you need more satellites to cover the same area. You also have the problem of tracking because of the speeds. The next most congested area is in the geostationary and geosynchronous orbits, shown in green over here. And a lot of the weather satellites and Earth observation satellites are located there. Also, there's a special version of the geosynchronous, referred to as geostationary, at precisely 35,785 kilometers. And that has the advantage of being able to point to one particular location on the Earth all the time, because it's tied in with the rotation, speed of rotation of the Earth. Sidereal time at precisely 23 hours and 56 minutes. The medium Earth orbits include, for example, GPS. They have a lot more coverage than the lower Earth orbits. There's also the high elliptical orbits, and they have the advantage in that they can cover some areas that the geosynchronous orbits cannot, as far as the northernmost portions of the northern hemisphere. So the Russians use, for example, the Molniya orbit, and Sirius Radio actually operates at the tundra orbit. And of course, with the elliptical orbits, the satellites move faster at perigee, closest to the Earth, and they slow down as they approach apogee, at the furthest point away from the Earth. So you get them swimming by with more coverage during the orbital period over the northern hemisphere. Now, this slide shows the relationship between altitude and orbital speed and orbital period. Now, monitoring and tracking orbiting objects is critical in protecting our assets and even lives. They involve a number of different tracking stations, ground-based optical, radio telescopes, radar systems, interferometers, and they're spread out throughout the globe, various countries, to be able to provide enough coverage to be able to continually track. And so that requires a lot of international government and commercial cooperation. The U.S. Space Surveillance Network is tasked with the responsibility of monitoring, tracking, and cataloging orbital objects, including active and inactive spacecraft and orbital debris. Satellite catalog, maintaining the accuracy of this catalog is critical. And it includes a list of the orbits and the information regarding the origin, date launched and country of launch, and the orbital data, position of the objects. And this is used in the surveillance system to determine not only the current position, but also projections on where the object is moving in time relative to other objects, so that predictions can be made of whether there's likelihood of a collision. So main criteria is accuracy of the orbital elements and frequency of updates, and information on who owns the satellite or object. And that's all a critical part of space situation awareness. Besides the US SSN SATCAT, which is the most comprehensive catalog, you have the ESA, the European Space Agency, has their catalog, and there's even a catalog available to the public issued by the Union of Concerned Citizens and Scientists. Other international organizations include that are involved in the coordination of the Earth orbiting objects and debris. Include the IADC, Interagency Space Debris Coordination Committee, and the UN Register of Objects Launched into Outer Space. So the UN keeps track of who's going to be launching when and what. So with the accuracy of the data being so critical, Space Force is now engaged in continuing with the Space Fence Radar System, progress on that. And that's a promising development, currently in testing phase. It's been designed by Lockheed Martin. And one facility that's pretty far along now in testing is the one on Marshall Islands, as shown here. It operates at higher frequency band, S-band, so that means that you get higher resolution in your detection, so you can sense the smaller microsatellites. And there's an improvement of the timeliness, so that perhaps we can close in on that time gap between when we see an object that's a potential problem to when we can warn somebody or take action to mitigate any problems. It's expected to be online by about 2021, next year. It costs about $1 billion. But for full potential of this, there'll probably need to be at least 2 other stations located at a couple other points on the Earth to give widespread operation and to actually get down to where we can detect objects the size of marble. A lot goes into collision avoidance. It's a very complex process, continually evolving. It involves prediction, assessment, and determining how to mitigate and what action to take. And of course, it depends on having the good data. And so conjunction assessment is made, identifying a close approach between 2 objects. Risk assessment is made for determining the percentage of probability of collision occurring, and then determining the mitigation plan. There's also physical protection of the ISS, for example, with Whipple shields to provide path for energy dispersion. We talked about mitigation to a certain degree. If, for example, in the event of a pressurized unit leaking, it's not too rapid, they may have time to coordinate with mission control and prepare re-entry into the Soyuz capsule. If there's plenty of time, it's just a slow leak, then they can just simply maybe close off the module and for repair for future space. crew. While eventually there might evolve some successful schemes for capturing or retrieving defunct satellites in the future, the better approach now is to factor into the design spacecraft improved ways to limit the creation of additional debris, adequately harden and protect the satellites by design, and develop plans for safe post-mission disposal. Again, the geosynchronous orbit is becoming congested. There aren't too many slots remaining. The International Telecommunications Unit is involved in handling applications for orbital slots. More recently, the separation between the orbital slots have closed in from 3 degrees to about 2 degrees, which still limits to 180 satellites operating at a particular frequency band. More satellites can operate in the same slot, but they need to be operating at different frequency bands to avoid any crosstalk issues. I came across an interesting article last month. It was in the space.com site. And it discussed the efforts of a loosely knit worldwide band of amateurs with the goal of monitoring whereabouts of secretive satellites that don't get entered into the SatCat and the other catalogs. The photo on the right is a little comical these days because it goes back to 1965. These amateurs actually use much more sophisticated techniques to do the tracking. Analyzing the Doppler shift from radio signals from various interferometers and radar instruments, radio telescope instruments. They've also been working with professional astronomers to try to determine how to handle the problems with SpaceX's reflections of their Starlink satellites. So they're trying to find ways of maybe reducing the reflectivity of the coating and see how that works out. Admittedly, I've only scratched the surface of this presentation, discovered some of the highlights of the broad aspects of critical issues. The continuation of our civilization, mankind's exploration of space depends on trying to have a grip on dealing with these issues. For me, for somebody like myself to really get a deeper understanding would require a lot more continuing effort. Been a member for a few years with AAI, and I'm really impressed with the wealth of hands-on knowledge that so many of the fellow members here have and are willing to share. And I know that they can maybe help me gain a better understanding of some of the technical issues if I want to look into it further. And the study of this overall issue, it covers all aspects of space exploration. Databases cover the whole history of each object ever launched. You're looking at the issues regarding the whole space environment and functioning of spacecraft, and just trying to keep aware of the latest fast-breaking developments is really nearly impossible task, especially with issues involved with commercialization. At this point, I'd like to thank Mary Duca for her support and encouragement, along with the AAI team members, in particular George Mathis and Aaron Zuckerman. I'm sorry, Aaron, involved with offering these remote presentations, which I've really enjoyed watching every Friday night. Not also to my son David and my brother-in-law Harry Jessel, who's also trying to help in some of the dry runs, maybe not as successfully as hoped, but anyway, thank you.
Thank you, Steve. Very interesting. And so I want to thank everyone for joining us tonight. I hope you will join us every Friday night at 8 o'clock online. Our presentation next week is going to be the Discovery Machine about the Hubble Space Telescope. So thank you again for joining us and wishing everyone clear skies.